Yeah. Okay, good evening to one and all. So, in the last class, we have discussed about the ramp type digital voltmeter, their advantage, disadvantages, principle of operation, block diagram. So, these are all the things what we have discussed. Right. Today, we'll go through the. Okay. So, these are the things what we have discussed in the last class, and now we are going to reduce these errors. So, the errors what we are having is superimposing of noise. So noise is there in the system or in the input, that the input should be clearly filtered. Okay. And advantages, easy technique, simple to operate like that. Okay. Now we'll go for the dual scope integrating type digital voltmeter. So here we are going to use two ramp signals instead of single ramp signal. So in the earlier case, we might have used either positive ramp or negative ramp, nothing but either the linearly increasing ramp or linearly decreasing ramp, like this. Okay. Let us say this is the unknown voltage. This is the dotted line is the unknown voltage. The solid line is the ramp signal, either increasing ramp. Okay, increasing ramp. Here this is decreasing ramp. Okay, so here we are going to use dual slope, dual scope, nothing but both increasing as well as decreasing we can use. Okay, superimposed noise also can be used to reduce here. So in the ramp technique, superimposed noise can cause large errors. So in the dual ramp technique, the noise is averaged. The noise is averaged by the positive and negative ramp. So because of using the two ramp signals, one is positive going ramp and second is the negative going ramp, we are going to get the averaging of that errors. So that is the method we are using. So just observe, this is the ramp. Okay, so here we can observe in this diagram we can find three ramp signals. Okay, let us go for a single ramp. So from 0 to, this is the peak, it has been reached in the time of t1. Okay, again it has been reduced in the time of t2 dash. Okay, if you are taking nothing but the first ramp, second ramp, third ramp. Okay, here three different ramp signals as used with different slopes. You can observe slope is proportional to ei. Ei is nothing but input voltage, input voltage, and er is nothing but reference voltage. Okay, so the linearly increasing ramp signal is proportional to the input voltage ei, nothing but the input, unknown input voltage is proportional to ei, and it will take t1 time, and the discharging time nothing but the coming to 0 time, we are going to use er is the reference. So the input voltage nothing but the slope is proportional to the reference voltage. So the reference voltage, if you observe the third one, this one. Okay, so it will take t1 time here. Okay, then from tn here to 0. So from the peak to 0, it has taken t2. The second ramp signal has taken t2 dash. Third ramp signal has taken t2 double dash, like that. So different time intervals we have taken. Okay, anyhow, at a time we are using one of it. Observe this block diagram. Okay, from this only we are going to get. So here also start pulse and stop pulse should be there. So because the counter has to count the number of pulses passing through the process. Okay, during the measurement of unknown input voltage. So here if you can observe, ei is the input voltage. Ei is the input voltage that is given to an integrator circuit. Strictly speaking, this is an integrator. So if you integrate constant, you will get a ramp signal. Keep in that mind. So if you are integrating the constant signal, then you are going to get ramp signal. So here we are going to get a ramp signal as output, and here the input is connected through switch SI. SI stands for input switch. SR stands for reference switch. Okay, here we are using a switch. Either we can connect to input signal or we may connect to the reference signal. So here we are taking input signal positive value and the reference signal as a negative value. Whenever we are measuring positive voltages, keep in that mind. If you are measuring a negative voltage, then by the time we can take the input voltage negative and the reference voltage positive. So because here we are going to increase ramp and decrease ramp, both are there. If you take the input value here, positive voltage, so this voltage is positive and reference voltage is negative. So for that reason we are representing negative voltage. If you are taking negative voltage as an input, it seems to be as like this. So negative input and positive reference, right? Like that we can make use of it. So any constant line, if it is passing through an integrator circuit, then we are going to get a ramp circuit. Okay, so here we are using a capacitor. Okay, during whenever the switch is connected to SI, nothing but this switch has been gets closed, then that voltage has been applied to the integrator circuit. Here the integrator circuit, as well as there is a capacitor is there. This capacitor starts charging. This capacitor starts charging. When it will stop, it will take a go, of course, up to t1 time it will charge. Up to t1 time it will charge. Once it reaches to the maximum charge, then this switch is gets opened and SR is this switch is gets closed. Nothing but now we are going to connect to the reference voltage. Then automatically what will happen? Okay, initially we are going to get the output voltage from the capacitor. That voltage is going to compare with the ground. Nothing but 0. So 0 and the ramp are going to be gets compared. So here we are using a comparator which is comparing with the 0 signal. Which is comparing with the 0 signal. So this comparator comparing the 0 signal, and if the input E naught is greater than 0, then automatically it will becomes 1. Comparator will be just like a relative operator, greater than or greater than, less than, like that. So if E naught is greater than 0, then comparator will give 1. So this 1 will be applied to the logical gate, AND gate 1. Okay, it is 1. And now from the clock oscillator we are going to get 0 1 0 1 0 1 like this. So this is 0 and this is 1. So AND gate, yesterday I said AND gate is nothing but a multiplier, 1 into 0 like that. So 1 into 0 1. So you are going to get here also these pulses. These pulses are going to be counted by this counter and display. Okay, so based on that, okay, because here the counter has to start and stop. The counter has to start and stop. So it is going to be controlled by a switch drive. So here the counter will start counting whenever we are getting 1 as an input. Now the counter is going to stop in the nothing but here during this T1 we are going to get N1 number of pulses. Okay, during this switch period, nothing but SR is gets connected, SI is gets opened, then the capacitor starts discharging. Then this voltage or this raised voltage has been starts discharging. So this during this discharge, there also we are going to get different time intervals. Okay, there we are going to get N2 time. So here for the reference, for the in this diagram, 3 different slopes has been considered. 3 different slopes has been considered. Actually, here every time we are using only one signal, one input signal, which is proportional to EI, the same which is proportional to minus ER while discharging. So charging and discharge, nothing but just only one diagram. So one increasing, one decreasing, that's all. So during increasing, the capacitor increasing, T1 time will be there. During capacitor decreasing, T2 time will be there. So during T1, we will have N1 number of pulses. So T1, N1 pulses. During T2, June. Yeah. During T2, N2 number of pulses. So start pulse and stop pulse is going to provide it from this, because whenever the input starts from zero, whenever the input starts from zero, so zero is greater than E naught is greater than zero, E naught is greater than zero, then we are going to get one as an output. That one has been given to the AND gate. So one and oscillators. So from this we are going to get, the counter will starts counting whenever it reaches to the maximum. Whenever it reaches to the maximum, then the reference signal, the input signal switch has been disconnected and the reference signal switch has been connected. By that time, now the capacitor starts discharging. Now the capacitor starts discharging. During the discharging, again the counter will starts counting that pulses also, and whenever it comes to zero, whenever this comes to zero, E naught and 0 are going to be gets compared. E naught and 0 are going to be gets compared. E naught equal to 0. Then automatically this comparator will enable again. So during this discharging duration, we are going to get N2 number of pulses. These are going to be controlled by this switch drive circuit. The switch drive circuit is going to control the switch on and off for the input signal as well as the reference signal. If input signal is connected, charging. Okay, if input signal is connected to the minus reference, nothing but negative reference value, then capacitor will start discharging. Okay, this is the procedure what we are using. So in N1 time, in T1 time, N1 number of pulses will be counted by the counter. In T2 time, N2 number of pulses will be counted by the counter. T1 is the time for the charging and T2 is the time for the discharging. Okay, so in this, during this timing, during this charging and discharging, we are going to get the number of pulses. These pulses are counted by the counter and it is going to be represent to the as the display unit. Okay, so this is the process of dual scope integrating type digital voltmeter. Is it clear? Whatever the explanation I have given, that I have gone through in these slides. So whatever the explanation I have given, that is there in this explanation. Okay, so this is how we are going to get the voltage. So now we'll go for the expressions. During charging, what is the output voltage? During discharging, what is the output voltage? And from that, we are going to calculate how much amount of input voltage we are applied, because finally our intention is to measure the input voltage. Okay, so here we are going to use the comparator. Okay, this circuit in the integrator circuit, E naught is the input value. Now the output voltage of the integrator is nothing but from 0 to T1, this is a charging period. 0 to T1 charging period. EI dt, nothing but the voltage has been increasing. Okay, so here minus 1 by RC, these are the constant terms. Okay, so here we are going to get EI T1 by RC, that is the output voltage for charging. Similarly, the output voltage for discharging, during discharging 0 to T2. Okay, so during this time minus ER T2 by RC. Now we are going to subtract these two equations during charging and discharging, because here observe 0 to T1, 0 to T2. What we need between T1 and T2, because 0 to T1, this is the voltage. Between 0 to T2, this is the voltage. So the waveform will be as of increasing and decreasing. So in this axis, okay, let us say from this from 0. Okay, let it be. Okay, so during this charging time, sorry, T1, T2. Okay, but we are measuring from 0. So 0 to T1 and again 0 to T2. If you want Okay, 0 to this position, let us say. Okay, so here what will happen? So if you want to get these two difference, nothing but we are going to calculate second expression minus first expression, nothing but from there we have calculated, and finally we are going to obtain what are the common terms like that. Okay, and finally you are going to get EI, nothing but the input voltage is equal to ER is the reference voltage divided into T2 divided by T1. So this is the expression what we are going to get as the output. So nothing but EI is nothing but the input voltage, this much amount of input voltage, where here ER is the reference voltage and T1 is the number of T1 is the charging time and T2 is the discharging time. So in T1 time we are having N1 number of pulses, in T2 time we are having N2 number of pulses. Now we are saying the same in terms of pulses. Okay, in the total time T1, okay, yes, earlier we have written that EI equal to ER into T2 divided by T1. So this is the expression what we are having. Now we are making in terms of capital T, nothing but the total the oscillator period that we can calculate. So N2 into T is nothing but, okay, T2 is nothing but N2 into capital T. Okay, and T1 is nothing but N1 into capital T. The total time N1 number of pulses. In total time N2 number of pulses. That is for T1 and T2. So that's what we are substituted, and we are going to get this as like this. So here TT will get cancelled. So that if you are representing EI is nothing but ER into N2 divided by N1. So the same formula is, this is in terms of time, this is in terms of number of pulses. Okay, so nothing but in the same time we are getting number of pulses, right? So that's the expression we are going to use. And E1 and N1 and ER are constant. Why you are saying N1 and ER are constant? ER is the reference voltage. Nothing but to get to that voltage, N1 number of pulses will be generated. So K1 we are representing, that is ER by N1. So this magnitude ER by N1 is K1. We are treating this as EI equal to K1 into N2. This is the expression what we are going to get, because N1 is the number of pulses. That's T1 time duration is fixed. Keep in that mind. The T1 time duration is fixed. So till T1 we are taking the number of pulses, and discharging we are going to calculate in the duration of T1 to T2, right? So from the expression we are going to calculate uh, averaging. So accuracy of the measured voltage is independent of the integrated time constant. Normally, time constant of integrated time constant is nothing but RC. Okay, so if you are observing the voltage EI is nothing but ER into N2 by N1. ER into N2 by N1. In this expression, we don't find R and C. So the value of integrated time constant is independent. So we need not worry about how much amount of resistance we are using, how much amount of capacitance there we are placing. Right? It is independent of the time constant of the integrator. And the time T1 and T2 are measured by the count of the clock pulses from N1 and N2. So during T1, N1 pulses. During T2, N2 pulses. Like that we can count. The counter will start counting. So whenever the counter starts, start counting the numbers. And whenever it reaches 0, stop the counting. So like that we can get N1, N2 number of pulses in the duration of T1 and T2. Now the clock oscillator period, the total period is capital T, nothing but T1 plus T2, nothing but N1 plus N2, like that. If we are representing in terms of pulses, right? And here N1 and ER are the constants. Okay. Okay, so the advantages. So the dual slope integrating method as having the excellent noise rejection because of the superimposed AC voltages are averaged in the process of integration. So in the integration, we are going to get the positive ramp and negative ramp. That's why we are going to get the averaging of that. And the speed and accuracy are readily varied according to the specific requirements. So here the speed and the readability, both are dependent or changing as like that. So these values are varying plus or minus 0.05% and 100 milliseconds speed. So we can get the reading of the data. Leela, how many bit 0.05% plus or minus 0.05% of error, and we are going to get the reading speed 100 millisecond. We will get the reading within 100 millisecond, nothing but as long as you are connecting or applying the voltage, you are going to get the voltage. Okay, 100 milliseconds, even we cannot observe clearly. And here, that is about the dual slope integrating type digital voltmeter. Now we'll move to the integration type. So it's a very much similar concept. Integration type is also a similar concept. So here the principle of operation is the voltage is going to be converted into frequency. The voltage is converting into frequency. So ramp type is, the principle is the voltage is converted into time, duration of time. In the integration type method, the voltage is converted into frequency. That is only the difference between the ramp type digital voltmeter and integrating type digital voltmeter. Right. Now observe here. Here also the similar concept what we are discussed earlier. Slope 1, slope 2, like that. So different slopes we can use. Okay. Reference signal, output signal, like that we can get. A constant input voltage is integrated and the slope of the output ramp is proportional to the input voltage. That's what I said. So the constant voltage has been given to the integrated circuit. Now I will show you the block diagram. Now observe here. EI is the, this is EI. EI is the input voltage. The input voltage is given to the RC, nothing but an integrator circuit. This integrated circuit is having R and C. As I said, these are independent of the time constant of the integrator. So here you are going to get output voltage, and that output voltage is compared with a comparator which has been taken with ER. So ER and E naught are going to be gets compared, either greater than or less than or equal to, like that. Okay, so greater than or less than, like that we can say, or greater than or equal to or less than, like that. So depending upon that, we are going to use here a digital frequency meter in additional, and how much the pulse generator will use, the number of counter, everything. Okay, so it is an a concept. Okay, here we are going to say about, this is the main concept. Okay, digital frequency meter is used to measure the clock frequency. Based on that, we can measure the output voltage. Okay, digital frequency meter is additional separate topic that we will discuss in detail later. So integration type of digital voltmeter, which is similar to the dual scope integrating type. There EI and ER compared at the driver circuit, and now here we are using comparator. So that is only the difference, and remaining things are same. The same what we have explained is given in terms of these wordings. Here T1 and T2. So during T1, number of pulses. During T2, number of pulses. Okay. So here voltage to frequency conversion. See, observe here. So the amount of reference voltage is dotted line. Here the reference voltage is dotted line. Okay. So ramp starts from 0 to maximum. At the time when it reaches to the reference voltage, T1 time duration will be there. So here the pulses start counting from the pulse generator, and T2 is the discharging time. So T1 and T2, like that. So on and off, on and off, on and off, like that. Okay. So during this x-axis, we are going to get these results. So here the voltage has been converted into frequency, because time is nothing but in terms of frequency, we can say. Time and frequency are similar terms. So we can call it as voltage to frequency conversion. Right. So similar expressions, EI equal to ER into T2 by T1. Okay. Or N2 by N1 also, we can say. And here ER and T2 are constants. In the dual slope integrating type, EI is fixed and N1 number of pulses are N1 are fixed. And now here it is E2, nothing but discharging time, nothing but the reference voltage to discharging time, nothing but here if you observe in this diagram, this time T2 is always fixed. Okay, only charging time will make the difference. Nothing but reaching to ER value will be changed. So a similar expressions in terms of EI we are going to calculate. So earlier we have used K1, K1 equal to ER into T1. Now we are using ER into T2. That is only the difference, right? And here we are having one disadvantage that it requires an excellent characteristics of linearity of the ramp signal. So every time we are saying the ramp signal, in the ramp signal should be properly linear. It should not vary. So okay, if you observe the ramp signal, so strictly, so it should not have any changes or like this. So strictly it will move as linearly. So linearity in the RAM is essential. Okay, or else sometimes it will be linear and some again changing like we observe. Up to here that slope is different. So up to here the slope is different. Again up to here the slope is different. It should not be like that. That linearity should be properly. Okay, and AC noise and supply noise are averaged because charging and discharging both you are taking increasing ramp as well as decreasing ramp. Now coming to the another topic, that is continuous balance digital voltmeter. So the continuous balance digital voltmeter is simple technique. Okay, I hope you might have completed the experiment potentiometer. Okay, sliding wire potentiometer. So if you observe the potentiometer circuit, there should be a reference supply. According to the reference, we are going to change the input. Okay, or else I will give one more example. Uh, mm, uh, let us take a scale. Okay, let us take a pen. We need to measure the length of the pen. So if the length of the pen is going to measure with the help of a scale which is calibrated, that scale should have calibration. We are going to compare with these two. If it is not there, we are moving the scale position. Okay, actually how we have to measure with the scale, that end or the tip of the pin should start from 0 on the scale. So if it is somewhere, then we are adjusting the scale position or the input position. So nothing but let us say, uh, let us take this is the pen and the scale. So both should start from 0 position, so that we are going to measure how much amount of length it is. If the scale is start from here, if the pen is from here, then there is a gap between these two. So it should not be like that. So we are going to change the position. So here the continuous balance type digital voltmeter is working based on the comparison of the input signal as well as the reference signal. Okay, the input signal and the reference signal. So depending upon the position of slider, depending upon the slider position. Okay, so input and the slider are going to be compared every time. So whenever these two are equal, okay, whenever these two are equal, then we are going to get zero error. Then automatically we are going to get the final output voltage and the output. Now observe, we'll go through the in detail. So here we are going to give the DC input voltage. The DC input voltage is fed to the input attenuator. Attenuator is used to filter any noise or superimposed in the input signal. Okay, DC signal ante manaki ila undali exact line, but the DC should not vary. It should not be like that. So we can use an attenuator to filter the changes. Then range switch. So how much range of input voltage you are measuring. So whether it's 10 volts range, 100 volts range, 1000 volts range, like that. According to that, we are using a range switch. Okay. Then we are going to use an overload protection and AC rejection. So overload protection means if the load, if the input is, let us say, if you are giving, if you are selected for 100 volts, if you are selected for 100 volts range, if the input is 120 volts, then automatically what we can say, 20 volts is the overload now. So the overload protection circuit will activate and it will stop proceeding to the next level. What happened? Right. Okay. Now, so overload protection. So if you are getting, if the range switch is at 100 volts, if you are getting 90 volts as input, so the 90 volts is within the range. So that's why we don't have any problem. So the voltage will be fed to the next circuit. And so your overload protection and AC rejection. If any, okay, let us say alternating currents. Okay, just like it may be not a pure DC, or sometimes if you are giving AC. Okay, so some AC rejection also will be takes place. So these circuit will be there, overload production and AC rejection will be there, and a pure DC voltage, only pure DC. Nothing but I am saying positive voltage. Okay, or don't say positive, pure DC. So this pure DC voltage is fed to a chopper circuit. Here this chopper circuit is a comparator. This chopper circuit is a comparator. So what is meant by comparator here? Here it is going to come. Here it is going to compare the input signal. Nothing but after this entire circuit, you are going to get the input here. So that input is compared with the reference supply. So normally, keep in that mind, whenever you are measuring any input signal, let us say I want to measure the length of the pen. Okay, so the scale should be moved accordingly, not the pen. Keep in that mind, because pen is nothing but the length of the pen is an unknown. Unknown things or unknown parameter data should never be altered. Okay, so the length of the pen, let us say this is around 15 centimeters. I think it is able to see. The length of the pen is 15 centimeters. Now we need to measure this with the scale. Whether you are selecting a short scale or long scale. Okay, just wait. Joshit, స్కేల్ ఉందా నాన్న? మీ దగ్గర స్కేల్ ఉంటుంది కదా, స్కేల్ ఇవ్వ మళ్ళీ ఇస్తాను. ఆ ప్లెయిన్ స్కేల్. స్మాల్ స్కేల్ అయినా పర్వాలేదు. త్వరగా. రైట్. Okay, now just observe this the scale. So okay, actually this is around approximately 15 centimeters. Let it be. So this is the scale what we are using, and this is the reference what we are having, and this is the input voltage what we need to be measured. Nothing but the length. Let us say half of the length. Okay, just I will go a small alignment. A tube is there. I want to measure with this. Okay, now this length should be fixed because we should never change this. And whenever you start measuring, you should start from 0 onwards. Okay, you should start from 0 onwards. And if you start from here, you will get the error. If you start from like this, you will get the error. So definitely start exactly from the 0 position. According to that, this reference voltage value has to be changed. Here not the scale, the voltage, because let us say the voltage is 10 volts. The voltage is 10 volts. The reference voltage, if you are taking 20 volts, okay, the reference voltage also has to bring to 10 volts. So 10 is the unknown, and the reference voltage if you made as equal. Okay, let us take here we are getting input voltage is 10 volts. Here the input voltage is 10 volts. From the reference supply, I will change the sliding position and I am going to get 10 volts here. If I am getting 15 volts, what will happen? There is an error. So comparator will compare these two values. So potentiometer value, here we are getting what we are getting, let us say 15 volts initially. So 10 and 15, there is an error. So that error is going to be gets amplified and again power amplifier and given to a servo motor. So the servo motor will have a control on the potentiometer as well as the display. Okay. Okay, now the error is 5 volts. Let us say error is 5 volts. Now this position is going to be changed. The precision potentiometer position is going to be gets changed from the servo motor. So servo motor handle is connected to the potentiometer terminal, so that whenever the servo motor starts rotating, the potentiometer position is going to be gets changed. Then it will reach to the 12 volts. Let us say 12 volts. Again, the input voltage is 10 volts. So initially, let us say 15 volts is the reference, and the input voltage is 10 volts. Error is 5 volts. Okay, now the potentiometer has changed somehow with the help of the servo motor. Now the voltage is 12 volts. Okay, the input voltage is 10 volts again. The error is 2 volts. Again, that error is going to be corrected by the servo motor. So potentiometer changed to 11 volts. Error is, sorry, input is 10 volts. Again, error is 11 volts. Now the input voltage is, let us, sir, the potentiometer has changed somehow. So it has gone for 9 volts. And the input voltage is 10 volts. The error is minus 1 volt. So negative voltage is there. Always error should be 0. Always error should be 0. Error equal to 0. So then automatically again the potentiometer servo motor will act accordingly. Again it reached to the 9.5. Let us say again 10 volts, 0.5 volts, minus 0.5. So after certain position variations, finally you will get 10 volts. Again the input voltage is 10 volts, you will get 0 volts. So whenever the comparator will give 0 volts, the 0 is amplified, again it is 0. Even it is power amplified, again it is 0. So that the servo motor will get 0 volts. So if you are getting 0 volt, the servo motor won't change the potentiometer position because the error has 0. And whenever it is getting 0, that voltage has been represented in nothing but whatever the reference voltage here we are given. Now the reference voltage is changing. Keep it in mind. Every time this is the input voltage what we are fixing. Nothing but the input voltage should never change because that is what we need to measure. So మనం మెజర్ చేసే వోల్టేజ్ ఎప్పుడు మారదు. ఇక్కడ రెఫరెన్స్ చేంజ్ చేస్తున్నాను. ఐఎమ్ ఈక్వేటింగ్ ద ఇన్పుట్ వోల్టేజ్ విత్ ద రెఫరెన్స్. సో రెఫరెన్స్ ఫిక్స్ చేసుకున్నాను. సరే, ఇన్పుట్ వోల్టేజ్ ఫిక్స్ చేసుకున్నాను. రెఫరెన్స్ వోల్టేజ్ ఇంక్రీజింగ్ చేసి ఫైనల్గా అల్టిమేట్గా వీఆర్ గెటింగ్ టు 0. లైక్ ఇంకా సింపుల్ ఎగ్జాంపుల్ చెప్తాను. Whenever you are going to the market, okay, because this example has to use for the next method. Anyhow, I am giving a similar example can be given here also. Balance లో ఒక సైడ్ వెయిట్ ప్లేస్ చేస్తారు, 1 kilogram of weight. సెకండ్ సైడ్ ప్రొడక్ట్స్, ఓకే, లెట్ us say యాపిల్ ఆర్ టమోటో. సో యాడ్ చేసుకుంటూ వెళ్తున్నారు. సో adding and removing like that we are going to do. And finally this 1 kg reference, okay, normally here the reference is what you can say, or else we can do one thing. I want 4 apples, let us say I want 4 apples. So 4 apples are going to place at one side. The voltage is here, nothing but the reference, nothing but the weight. That weight I am changing, either it may be at 200 grams, 400 grams, 800 grams, like that. Okay, so that we are changing the weights accordingly, and finally we are getting equal to 0. So whenever the simple balance is equal, nothing but 0 error. So that we can say, yes, this much amount of weight is there. So the continuous balance type voltmeter will work out like this. Okay, and this comparator or this chopper circuit is going to be driven by a AC drive circuit. So normal AC supply we are going to use. Based on that, we are going to operate this entire process. So a very simple method. So the reference is going to be changed accordingly to map or to match with the unknown input. So in the table what we have written, this is reference voltage. This is the input voltage. Always change. This is the error. So reference minus input equal to error. Reference minus input is equal to error. So reference voltage we are changing. The reference voltage changing has been done by the servo motor. The servo motor will change the position of the or the voltage magnitude of the reference supply, so that we are going to get the reference voltage. So reference voltage is compared with the unknown voltage, nothing but the input voltage. Error can be generated. That error can be amplified with the help of preamplifier and power amplifier and given to the servo motor. That servo motor will move the based on the error. If the error is more, it will change more position of the potentiometer. Okay, if the error is less change will be done. Okay, so depending upon the error, if error is 0, then the servo motor won't change any position of the potentiometer, so that the same voltage will be updated. So during this process, how much amount of voltage we can get? Whenever we are getting 0, that voltage will be appeared here. Now whatever the reference voltage, whenever we are getting zero error, the reference voltage is nothing but displayed on the display unit. Okay, because reference voltage is a known value, input voltage is an unknown value. So whenever these two are equal, the error is 0. That error, whenever the error is 0, the servo motor won't work. It won't move the potentiometer. So that whatever the reference voltage by that time, that voltage will be represented as the display in the display unit. Okay, this is about the continuous balance type digital voltmeter, right? So the same explanation what I have given is there in this text. Okay. And here we'll say one thing, the average reading time is 2 seconds here. Okay, nothing but it has to change the value. Here mechanical position changes are there because a servo motor is there. That servo motor has to change the position of the reference voltages. Okay, so because of that, it will take certain time. It will take certain time to change the position. Okay, to change the position of the reference voltage level. So that's why mechanical movement has to be taken place. For that, it will take certain time to match finally with the input voltage. So that's what reference voltage, input voltage. So reference minus input is equal to error. So reference is, let us say, initially 15 volts, error input is 10 volts, error 5 volts. So it should come from 15 to 10 volts. 10 minus 10 volt equal to 0. So during this process, because of this duration, the servo motor will work. Servo motor will work to change the reference signal. So for that, it has taken 2 seconds of time. Okay, so compared with the earlier digital meters, so that may be a RAM type digital voltmeter, dual slope, or dual scope, or integrating type, whatever it may be. So there it will take high speed, but whereas here it will take 2 seconds of time, right? Now we'll move to the another topic, that is microprocessor based RAM type digital voltmeter. Okay, just wait for 2 minutes. I will take water. So just observe this block diagram. So microprocessor based RAM type digital voltmeter. This is fourth type of water in glass thing. Fourth type method. So RAM type, we have actually integrating type is in our syllabus, as well as dual slope is also a part of that. So that's why I have covered both. Right. Now we'll go through with the microprocessor based RAM type digital voltmeter. So whatever the RAM type digital voltmeter we have discussed in the very beginning of the classes, the same method here also we are using, but only the thing is here we are operating through a microprocessor system. Okay, so you can observe various blocks which are embedded in the microprocessor based RAM type digital voltmeter. We can see these blocks. the input, nothing but the unknown value. So unknown input. So this unknown input voltage, input signal conditioner. Input signal conditioner consisting of ranging switches, attenuators, noise rejection, etc., etc., etc. So finally, we are going to give the input voltage, unknown input voltage as Vx. Vx is nothing but the unknown input voltage. Okay, and here we are using one multiplexer. Multiplexer means many input, single output. Many input, single output. So mux, multiplexer means mux, multiple inputs. So here we are getting three inputs from, one is from the ground, nothing but 0 volt. Second is the input voltage Vx, and third is the reference voltage Vr. So three inputs are we are getting for the multiplexer: 0 volt, Vx, unknown input voltage, and third one is V reference. Okay, so 0 volt, this nothing but volt. Okay, 0, nothing but ground is nothing but 0. 0 volts, unknown input voltage, reference voltage. Three inputs we are getting. So position 1, position 2, and position 3. Also, it is getting the microprocessor system input. So these input. So totally around 4 inputs we are getting, and we are getting one output, that is the output of this multiplexer is given to a comparator at the position 1. Okay, right. Now to the comparator we are going to get the input from the microprocessor system. This input, nothing but the multiplexer has having three inputs. One is ground, second is the unknown input voltage, and third is the reference voltage. The comparator is getting two inputs. One is the output from the multiplexer and reference input. Sorry, ramp voltage. Ramp voltage. VR is nothing but ramp voltage here. Okay, so this comparator getting either 0, either Vx, either Vr, and as the first input, and second input is Vr, ramp voltage. So reference voltage and ramp voltage. So here we are going to, this comparator is going to compare. So at a time we are getting either 0 or Vx or Vr. Three won't become at a time. Okay, depending upon the input value we are going to use. And that comparator output value is given to the microprocessor system for further process. Okay, anyhow, that I will go through what is what. Okay, and there is a feedback system will be there. The microprocessor system also will give a feedback to the input, and how these values are going to be gets altered accordingly. Right, and finally we are going to get the reading out. So now we'll see the process how it is there. The multiplexer is going to get the three inputs. That is one, first input is 0 volts, nothing but ground. Second input is Vx, nothing but the unknown input voltage, and third input is reference voltage. So either 0 or unknown input or reference input. So these are the inputs, and the output will be any one will be selected based on the microprocessor system. So this microprocessor system is getting the input from the comparator only. So comparator will give certain input. How the microprocessor system has to select work, nothing but whether the multiplexer has to select for 1 or 2 or 3. అంటే 0 volt అప్లై చేయాలా, ఇన్పుట్ వోల్టేజ్ అప్లై చేయాలా, రెఫరెన్స్ వోల్టేజ్ అప్లై చేయాలనేది మైక్రోప్రాసెసర్ సిస్టమ్ డిసైడ్ చేస్తుంది. సో ద అవుట్పుట్ ఆఫ్ దిస్ multiplexer will be either 0 or Vx or Vr. That will be decided by this microprocessor system based on these comparators. Okay, now if you are getting 0, now 0 and reference are compared. Okay, if the microprocessor system has selected 0, let us say, now the comparator is getting 0 and Vr. So 0 and Vr are going to be compared. Vr is nothing but ramp voltage. So ramp voltage is compared with the, so always VR is the input for the second terminal of the comparator. So 0 and VR are going to be gets compared. So whenever the reference voltage reaches to, whenever the ramp voltage reaches to 0, nothing but ramp, here you are taking increasing, decreasing, increasing, decreasing like this. Or else we can use a certain time gap also. Increasing, decreasing, certain time duration gap, again increasing, decreasing, gap, increasing, decreasing, gap like that. So anything that depends upon the system what we are using. Okay, so ramp whenever it comes, okay, so the comparator is going to compare this 0 and ramp voltage. Okay, the next the input is Vx. Vx is compared with ramp voltage. V reference is compared with ramp voltage. So the ramp voltage is being compared every time with either 0 or unknown voltage or reference voltage. So three comparisons has to be taken place here. First comparison with the 0, second comparison with the Vx unknown voltage, and third comparison with the reference voltage. So in this diagram, of course, this is 0. There is certain reference voltage. There is certain nothing but this line is input voltage. There is certain reference voltage. So three comparisons are going to be gets taken. So initially the microprocessor system will reset. Okay, when the ramp signal, ramp signal increasing, decreasing, increasing, decreasing, it is going to take just like a sawtooth signal. So as the ramp is go on increasing, again reach to the reference value. Okay, then the microprocessor system will send a clear signal. To clear the ramp voltage. Nothing but ramp will come to 0. Ramp 1 comes to 0. Then again 0 is compared with 0, or 0 is compared with Vx, or 0 is compared with VR like that. So increasing, decreasing, increasing, decreasing like that. So every time the microprocessor system will give clear signal to the ramp voltage initially. So 0 value is compared with, will be as the input with the at the comparator. Now whenever the input is applied, now the voltage will be applied. Nothing but Vx will be appeared. That Vx value is compared with now VR. Now comparison will takes place. As based on the comparison, the time duration is going to measured by the microprocessor system. Again, it is whenever it reaches to the reference signal maximum value. So initially 0, input comparison and reference comparison. Observe here, 3 dots are there. 3 dots. So input 0 comparison, input comparison, reference comparison. So during these times, the microprocessor system will makes the counters to count the number of pulses during the durations. So that counter will count that, and that will be given to the readout. So during the increasing period and during the decreasing period also it will count. So during the durations, the microprocessor system will work accordingly, and it is going to measure how many number of pulses are being taken or counted by the counter, and that will be displayed in the readout. So that process is given in this system. Observe here. So 0 VM, nothing but the measured voltage, or we can say maximum voltage, up to the maximum voltage. Again come to 0 position. Okay, so like that this process will takes place. So 0, maximum, minimum, maximum, minimum, like that. So and here there is during this minimum to maximum. So where VM is the maximum voltage, during this minimum, nothing but the voltage will rise to maximum value. So we are nothing but the ramp voltage. This ramp voltage will rise to the full scale reading, where VM is nothing but a full scale reading. So up to full scale reading, we can vary. During that time, observe in the second cycle, 0. This is the amount of input voltage. This and nothing but here there is a comparison. And here there is a FV, nothing but a full scale reading. Maximum or full scale, let it be. Of course, these two are similar. Okay, third comparison. So these three comparison between these things. So we will find the durations. How much duration it will take for 0 output it will take for Vx, how much time it will take for the maximum. So T1, T2, T3 during the time duration, number of pulses. So TR raise time or retrace time, like that we can call it as, right? So the process will take 0 unknown input voltage, maximum voltage, like this comparison. Okay, the same has been explained in these diagrams, and this explanation has been given for this. So just go through and try to understand what I have explained in this. So there is some expression will be there during the time. So 2 minutes will take. So we'll wind up this class. Vx unknown input voltage. So N1, N2, N3, three different times are there. Delta T1, delta T2, delta T3. Okay, here N1 number of pulses, N2 number of pulses, N3 number of pulses. So here we are going to use lines. So C into N2 minus N1 divided by N3 minus N1. So from this expression, we are going to calculate where C is the coefficient of dependent on the characteristics of the instrument. Okay, just like a constant. Okay, so anyhow, it is depending upon the number of pulses. So N2 minus N1 divided by N3 minus N1. So from this expression, we are going to calculate Vx, nothing but the input voltage. So here we are going to calculate if it is in terms of time as well as the full scale reading. So Vx by Vfs can be calculated as in terms of delta T2 by delta T1 divided by delta T3 minus delta T1. Similarly, we can calculate in terms of full scale value also, we can represent, right? And the advantage is the scale size remains constant, and due to the zero drift correction and maximum, so nothing but the speed of the accuracy is very high, and there is no drift, nothing but there is no change, even there is no change in the input, so drift condition will not be occurred, and accuracy of the instrument is not affected by the time, because even though temperature instability is also, it will not change. So good repeatability in the switching instance, even in the presence of noise and interference also. And because of the ramp approaches, the point at which the comparator operates always the same side and always at the same rate, nothing but in the same slope we can prefer. And disadvantage is if sometimes the microprocessor system may be inferred due to the electromagnetic interference with the another signals. So this successive approximation technique that we will see tomorrow in the class. So for E1 section, the first 2 hours I will take, and I am going to cover the successive approximation method. And third hour, Priyanka ma'am will take for the bridges circuit for E1. For E2, your timetable will be as usual, right? Now I am going to end this class. Okay. Do you have any doubts? So if you have any doubt, you can send the text on the chat box.